Hi, I'm Craig Smith, and this is Eye on AI. This episode is again sponsored by Paperspace, which provides the tools for end-to-end management of machine learning workflows. Its platform comes with dedicated GPUs in the cloud. Check them out at paperspace.com. There's been a raging debate in the past few years between the symbolists and the connectionists about the future of artificial intelligence. The symbolists say the traditional, explainable, logic-based approaches still hold tremendous promise, while the connectionists say that the power of deep learning, despite its current opacity and the narrow field of its application, holds the key to more general forms of machine intelligence. This week I speak with David Cox, who runs the MIT-IBM Watson AI Lab, which is blending the two traditions in what they are calling neuro-symbolic AI, in hopes of moving the combined field forward. As part of that effort, his team has developed Cleverer, a new video dataset for teaching machines to reason about causal relationships. It's a promising direction, and I hope you find the conversation as intriguing as I did. Tell me a little bit about yourself. I'm always kind of curious how people ended up in such a rarefied world.
Well, I got here by accident. There was no plan. I just stumbled through my life until I got here. I'm a recovering academic, so I was a professor at Harvard for 10 years, and I actually started my career as a neuroscientist. I was actually studying brains of monkeys, and we were trying to understand how the brain works, but along the way, it was the right time to start thinking about using GPUs, which were not general purpose computing devices at the time, to start thinking about how we would model brains. And then that led me down the rabbit hole to eventually a career in AI. And then IBM showed up and said, how would you like to put a zero after all the numbers? And I said, sure, that sounds great. And now I run this somewhat unique lab, IBM, together with MIT, where we're really taking seriously the idea of, how do we go to the next level with AI? Not just apply AI to applications, but really ask where in the space of applications can't we go today because we just don't have the right techniques. Now that I'm at MIT, I did my PhD at MIT, so it's a little bit coming back to my roots, but work with a lot of people in the Department of Brain and Cognitive Sciences like Josh Tenenbaum, who's really a cognitive scientist, but who also crosses over into AI. And there's just such a rich interplay of ideas between AI and neuroscience. It's exciting. So the broader agenda of neuro-symbolic AI is really about how do we take these kind of two great traditions of AI, and one that's enjoyed a resurgence lately. So neural networks, artificial neural networks, have now been kind of rebranded as deep learning, and they've become very powerful. They were enabled by the digitalization of the world. We have lots of data, we have lots of compute, and that's what made the fundamental techniques, which were largely worked out in the 80s and even before, to really work at scale, together with symbolic AI, the idea that we have kind of symbols and manipulation of those symbols, to combine them together. And we're really interested in all the different ways you can combine those things. So the first piece that I think is important is simply just the recognition that there are symbols and that the symbols are important, right? That there are dyed-in-the-wool neural network, devotees like, say, Yoshua Bengio will say things like, hey, what we really need to do is find low-dimensional, sparse, causal, representations that reflect the causal relationships in the world. They're resistant to use the word symbol, but when you get right down to it, if you're talking about reducing the world to a very, very low-dimensional, set of entities that have relationships to each other that are causally related, very quickly, what you're describing, whether you want to say the word or not, is symbols, right? Like, if it walks like a symbol and it quacks like a symbol, I think we should all accept that it's a symbol. One of the problems with symbolic AI has always been, well, if you assume that the symbols are there from the start, how did you get them? Where did they come from? You kind of assumed away the hard part, which was getting from the messiness of the real world, like a picture, to a symbol, or getting from the messiness of a natural language question to a symbolic representation, like a program. That's the starting point, but there wasn't a good answer. Now, there's one piece of this is, well, neural networks, it turns out, are actually a great candidate for getting you from the world of the messiness of the real world and the images and the messiness of natural language to symbols. So in many ways, that's one piece of the puzzle. It's like, hey, this is a great way of extracting these symbols. Now, once you have those symbols, what's some of the visual question answering work, that Josh's team did with people on my team, well, some of the power of that is, if you have something that's fundamentally symbolic, like simple logical operations and predicates, if you have the symbols, why not just solve it symbolically? We have tools for doing that. They're incredibly powerful, incredibly precise. They're fundamentally transacting in the units that we as humans like to operate in. We like to operate in terms of symbols. Like I want you to talk about the entities in an image, and I want to talk about the relationships, and I want to use logical statements about them. That's the language of my thought at some level. So if I'm going to understand a machine and understand its decision, then that's a very powerful way to do it. Now, there's another place where, I should say also, there's an awful lot of different kinds of symbolic tools we have, from logic for everything from theorem proving to first order and higher order logics they're very powerful. We have things like planning. So planning is a symbolic method for deciding a series of actions that can get you from state you're in to a goal you want to get to. That's been around for a long time, very rich field. So if we can use neural networks to get from the world that we start with, our actual inputs, to a symbolic world, we have this wealth of tools that we can use. And that's powerful. But then there's another piece where we can also use neural networks to help out with the symbolic parts. And this is a part where I think there's some debate over whether we should, if you accept that symbols are the right things for us to be operating in terms of, well, maybe we should build neural network systems that can manipulate those symbols and can do logic, maybe even can do planning and things like that. So there is a field of research that we engage in as well about saying, how do we use neural networks to help do those kinds of symbolic operations? So, don't use the old symbolic methods, but build neural networks that can do similar things. And that's powerful. And then there's ways of augmenting, many symbolic methods are fundamentally about search. So how do you search through a set of different possibilities to find the right answer in a precise way? In many cases, neural networks can also be used to give those symbolic search algorithms a sense of intuition such that they can get to the answer faster or more attractively. So I think where we are really is, there's a very simple setup, which is about getting from the world to symbols. And then there's all kinds of different ways in which neural networks can be used to augment and mix with ideas from symbolic AI. And that mixing, I think it's anybody's guess which parts will emerge as being essential. But I think fundamentally having the richness of representation that symbols give us, the relationships, logic, positionality, those things are here to stay no matter what. And then really it's about how do we use this sort of amazing toolbox that we've developed over decades, from these two different traditions, and combine them and recombine them in ways that are sort of maximally powerful.
You talk a little bit about this work of the Clever data set, how that built on the Clever data set and the experiments that you've been doing.
Yeah, so Clever is about moving the ball forward in terms of sort of common sense questions we can answer about video and the relationships between objects. It descends from a data set called Clever.
Right.
And Clever was designed in many ways to illustrate a problem with deep learning. You have a very simple setting where you have simple objects like cubes and cylinders and spheres, and the data set was generated. So you decide where the objects are, you render a picture, just like rendering a picture in a Pixar movie. And then because you generated that image, you can also ask all kinds of relational questions about it. Like, what is the color of the cylinder that's to the right of the sphere? And you know the answer because you generated the data set. Now, the interesting thing about those kinds of questions is even though those are trivial for us to answer, even a child can answer questions about these kinds of relationships. To train an end-to-end neural network, and end-to-end is the watchword for deep learning. You really want to go from what you have to what you want or whatever you want, and you put a neural network in between and you get out of the way, right? You don't put anything in the middle. And then you train that with lots and lots of data and you get your answer. The problem is with data sets like Clever, you need to have enormous amounts of training data to get them to train in an end-to-end way with any level of accuracy. And even if you have like 800,000 examples, say, you're still not going to get 100% accuracy going from a question and a picture to what's the answer to that question. And then the reason for it is interesting. And that has to do, we think, with this fact that what's really happening is that there's a compositional element to it, right? So a deep learning system is trying to learn, it's fundamentally a nonlinear function approximator, which is just a fancy way of saying you're mapping from what you have to what you want. And it can be a complex relationship, but there's really a distribution of things. And for deep networks to work, you have to kind of sample all the corners of the space to some degree. And they generalize surprisingly well the things that are close to what they've seen before. But if you don't cover the space of all the possible combinations and permutations, they can really struggle. And what Clever really does is it encapsulates a case where there really are many, an explosion of the number of possible combinations and permutations. And neural networks struggle to learn, and you need to have huge amounts of supervision to get it done. Yep. Now, what Josh Tenenbaum together with our own Chuang Gan did was to add in a dash of symbolic logic, which gives it that compositionality. So you're sort of building in from the ground up that, hey, we're going to have a system that has a rich, expressive way of dealing with that compositionality. So you don't have to see every combination and permutation to make things work. And when you do that, a bunch of magical things happen. All of a sudden, you need a fraction of the amount of data. You can get by with 1% of the data and do as well as many deep learning approaches. If you have just 10% of the amount of data, you can just completely solve the problem. And of course, where previously it was designed to be hard for neural networks by themselves to solve, if you add a dash of symbolic processing, all of a sudden you've got it. You can get effectively perfect performance. And then the last piece, which is really magical, is you have something that's intrinsically explainable, because you're going from a question to a symbolic program, which operates on the symbolic representation of the data. And you just walk through and say, did this get the right answer for the right reason? And then now that Clever solved, what Clever is an extension. Say, well, let's take it to the next step. A big part of human reasoning is not just being able to identify what's there, basic sort of descriptive questions like, is the cylinder to the left of the cube? But you want to say, hey, if the ball rolls into the scene and bumps into something and the cube moves, why did the cube move? Can we explain the reasons why things happen? Can we attribute causes and effects? Can we do counterfactuals? Can we say, what would have happened if the ball hadn't been there? What would have happened instead? And then we were really getting into increasingly more and more sophisticated ways of being able to reason about the world. And I think this is ultimately a direction that's going to bring a lot of value for real world applications of AI.
Walk me through one example where the neural nets are being applied, where the symbolic logic is being applied.
Maybe it'll be easier if we start with Clever, and then we can work up to Cleverer. So the setup of the problem is we have a picture with all these objects in it, and we have a question. There are an equal number of metallic things and large things. Straightforward enough, and the answer, depending on the picture, is yes or no, right? So in the traditional deep learning context, what you would do is you take what you have. I have a question, which is natural language, and I have a picture, and I'm going to put them into a neural network. I'm going to feed that through, and I'm going to map it to what I want, which is the answer yes, and I'm going to turn that crank a jillion times, right? That's the standard end-to-end model. What the team did for Clever, which I think was clever, was to take, let's break apart that question. Are there an equal number of metallic things and large things? Well, you can take the question and we can put it into a recurrent neural network. They're good at processing natural language. It's the best tools we have available. So let's use them for their strengths. But instead of transforming that sentence into, say, another language, neural translation, something we know how to do, or instead of rating it, for its sentiment or whatever, let's instead translate the sentence, the sequence of words, into a program, which is going to give us a set of steps. And if you look at the question, are there an equal number of metallic things and large things? Okay, well, there's a series of steps. We need to look at the scene. It's asking about metallic things. Okay, let's use our visual system. And now we're going to use another neural network. We're going to use a convolutional neural network because we know that those are great at doing vision. So we process the question. We know it's asking about something about large. We filter for the large objects. And then it's asking us something about the metallic objects. We filter for the metallic objects. And then we ask if they're equal. Are they an equal number? And that's a logical operation, fundamentally.
Right.
You're going to compare this number or compare that number. So what we do is we translate the question into a program. We run the program on the output of a convolutional neural network that de-renders the image into a structured representation of what's in the scene. And then we step through the symbolic program. And the magic of this thing is that the whole thing is trained jointly. So it is going to learn. It's not just like we're going to bolt pre-trained neural networks onto a symbolic process system, but rather we're going to combine the things together and we're going to use reinforcement learning such that the computer vision part learns to better parse the world into objects by virtue of being part of this system. When it gets the right answer, it gets reward. And that, encourages whatever the neural network was doing. And then we're also going to encourage, the translation of the sentence into a program that we're going to run. And again, because that's trained together with this reinforcement learning approach, the neural network part learns to do a better job of turning the natural language into a program by virtue of being part of this joint system together. And when you put those systems together, then basically the system doesn't have to learn every possible combination and permutation of this object being next to that object. It can leverage concepts and the composition of these different parts in a very powerful way. And that's ultimately, I think, the magic of neuro-symbolic systems.
What data set are you using on the semantic side that gives definitions to specific words like metallic?
Okay, so that's a great question. So in the first neuro-symbolic visual question answering paper, which is basically what I just described, a lot of those concepts were hard-coded. So you just needed to know there was something called metallic, and that was predefined. Now, of course, that's obviously not where we want to stop, because one of the concerns about symbolic processing is how do you build up lots and lots and lots of symbolic knowledge? You'd like to be able to learn that from the world. So the next paper that team produced, again, this is a collaboration between Josh Tenenbaum and some folks in my group and some other folks at other places. They developed something called the neuro-symbolic concept learner, and this is a system now that can learn to acquire new concepts. So it's using neural networks and it's using tools of deep learning to be able to more flexibly learn, sort of imagine new values of the property of color. We know about red and we know about green, but we don't know about blue yet, or we invent a new color, aquamarine that it hasn't seen before. It can learn from experience to incorporate those new concepts and then still be able to use symbolic reasoning on top of these new concepts. So they're increasingly making the system more and more and more flexible. And I think that's actually a really interesting thing, because that's kind of our roadmap at some level. We want to move from systems that require lots of human knowledge and human hand engineering and move towards increasingly more and more autonomous systems where they can learn new concepts autonomously. They can learn new tasks autonomously. And I think this is a big piece of the unsupervised learning drive, is we want to increasingly have systems that don't require huge amounts of careful handcrafting and development by, frankly, very expensive people who've trained for a long time to twiddle the parameters. We really want to have systems that are much more flexible and fluid, that can drop into an environment. They can learn new concepts as they need. They can learn new tasks and increasingly build on what's been done before. And that's really the progression of what we've been doing from the early visual question answering work with Clever to the neuro-symbolic concept learner that the team did to things like Clever, which is pushing the envelope. Basically Clever is solved. So let's move beyond that and start saying, can we look at systems that have dynamics? They actually have physics to them, and start to learn intuitions about that, and be able to reason about things, be able to reason about counterfactuals, things that didn't happen, what would happen if something had been different. And that's kind of, an increasing level of sophistication that I think as a field, AI needs to drive towards if we're really going to have the impact we want to have on everyone's daily lives, solving hard problems. A lot of these hard problems have that quality of being much more like puzzles that we need to figure out than simple mappings between what we have and what we want.
Yeah. And I have questions about Clever, but on this idea of building up from a limited labeled data set, is there an estimate of the minimum amount of labeled data to start a system? I mean, I'm just thinking, a child learns a certain amount of language from its parents or its family, but then starts inferring language exactly in the way that you say. The mother asks for something and the child looks around and it knows the names of all these other objects, but it sees something that it doesn't know the name to, and it infers that that's what the mother is asking for. So is there sort of a minimum amount of data that's required to get this started? And then, in an imaginary world, you would have this system that would run forever and gradually build up a body of conceptual knowledge.
Yeah, I mean, I don't know if we have any way of saying theoretically what the minimum is, but we do have something like an existence proof of a bound. We know how much it takes for a child to learn about the world. We know how development progresses and how children learn some of these things. That we use the word common sense to refer to a lot of this. Our basic underlying knowledge of the affordances of how things relate to each other in the world, of basic physics, things that we never write down. Actually, this is one of the big problems with purely supervised approaches. You can imagine ingesting all the text of the world to try and learn everything. And the problem is that actually we don't write down a lot of things. When Gary Marcus gives a great example of, if you're hammering a nail into the floor, what's the orientation of the nail? And it's like, well, we know what floors are. We know what hammering looks like. We can picture in our mind's eye what that would look like. And we know that the nail is vertical. But you're not going to find, with the exception of the fact that Gary's now written about that, you're not going to find that kind of thing written anywhere. You're not going to be able to search Wikipedia and, find the article on hammering nails into floors and what's the orientation of the nail, because that's something we take for granted. Yeah. And that base level of knowledge is something that we don't really have incorporated into AI, and we don't really have a great story yet about how we're going to do it. But this is really important that a lot of us are working on. In fact, there's a DARPA program called Machine Common Sense that we're participating in together with MIT and Stanford and Harvard. And one of the interesting properties there, apropos the question of, so what's the minimum required experience to acquire some of this knowledge? One of the interesting requirements of that program is that they actually have a team of evaluators that the government has hired to evaluate how well we're doing. And it includes child psychologists, developmental psychologists. And our own team was required to. And we actually have Liz Spelke and Rebecca Sachs, and Tomer Ullman, people who actually do experiments with human babies and children to learn about how they develop over time some of these common sense notions. And what we're doing is then building AI agents that live in a simulated environment and are able to acquire some of these common sense notions. So, I think it's an interesting intersection then of cognitive science and developmental science in particular, and AI, where we're sort of asking, can we get our AI systems to the point where, with comparable amounts of exposure to the world, can they acquire that same baseline level of common sense knowledge upon which you can build the scaffolding of ever increasing knowledge and conceptual understanding and frameworks and sort of mental models, which then ultimately I think give rise to the kind of intelligence we really need if we're going to move to the next level with AI. I think where everyone's going, where the field needs to go, is to reduce the dependency on so much labeled training data, because If you look at it from an application standpoint, there are always going to be cases where you rely on past experience. Pre-trained models on ImageNet is a great example where you can use those features that were trained in one way with lots of data for some other purpose. So I think there are going to be elements of that, but we just need to dramatically reduce the amount of actual supervision you need.
Yeah. LeCun is predicting futures with video with no supervision or no labeled data. It's just training the system on millions of YouTube videos so that it develops an understanding of the world.
When I was at Harvard, we developed something called the PredNet, which is exactly in the same frame and in the same model, where it's you could think of it as being sort of self-supervised.
Right.
It's you take in a video stream and you're trying to predict what the next frame is going to look like, and that's a very powerful way to learn about the structure of the world. And we do that too. I mean, ultimately, you're going to want systems that can take mixtures. If you have supervision, you want to have it. You want to be able to learn about structure by just observing streams of data. And increasingly, one of the things that neuro-symbolic potentially gives you also is to be able to sort of incorporate external knowledge as well. So, if a human can write it down, you hopefully can add into account as well. Jan had this idea, this picture, this cake, where most of it was unsupervised, and then the supervision was sort of the icing on the cake, and the reinforcement was the cherry on top. And I think that kind of maybe antagonized the reinforcement learning people a little bit, but I think the spirit is sort of right. If you look at a human, where do we mostly learn from? It's very rare that we get somebody telling us, or showing us flashcards or something. We observe the world around us. We get lots of exposure like that. Very occasionally we get rewards, like something good happens and I get a reward and I can try and figure out why I got that reward and optimize it. But the vast majority of what we get is that unsupervised part. So I think that's the right picture. From a practical standpoint, we want to build systems that can take in all different kinds of information. If you have supervision available to prime the pump, so much the better. If you can observe the world and learn the structure, so much the better. If you can build in structures and biases to the architecture that incorporate things we just know. Yeah. The structure of a convolutional neural network encapsulates that idea and makes it so you can leverage that so you don't have to have so many training examples to learn. That's one of the great successes in deep learning. But there's lots of structure that we can know and we can build in from the get-go. And the more of those you can incorporate, obviously, that's also gonna be very powerful. The key thing with neuro-symbolic for us is really this idea of symbols. What's really magical about them is your ability to flexibly compose them and recompose them and have more richer, more structured representation, including things like program. We do program induction, where you translate natural language, for instance, into a symbolic program. And having some biases around the structure of what those programs can look like can be extremely powerful for augmenting systems that learn from observation.
The Clever data set was how large, and was that of static images or was that video as well?
So the Clever data set is all video. I don't actually remember off the top of my head exactly how many clips we have in that, but in principle, it's an infinitely generatable source, right? So what these data sets are is a way of generating images, generating videos where what ground truth is. What's happening. You can ask these sort of relational questions and counterfactual questions and descriptive questions, and then back out from that. You use that as a tool. The Clever data set is a bunch of pictures paired with questions and their answers.
Right.
So you need to take in a picture and a question and say what the answer is.
Right.
So in the case of Clever, you're basically running simulations that you have, a simple physics engine that you can render images and objects. So to generate a question of what would have happened if the cube hadn't been there, you rerun the simulation, without the cube there and run the physics, and then you can determine those answers. So there's a little bit of an art to producing some details to how you produce a good set of good questions that are interesting questions. But fundamentally, the spirit of these data sets is let's simplify the domain greatly. let's generate the images so we know what the answers are, so we can generate a large set to test over. Like the counterpoint would be to do something like you'd have to do a naturalistic experiment where you collected lots of real videos in the world, and things happened or they didn't happen, and you'd have to have people annotate them, and it's a huge amount of effort. And in the domain of visual question answering, some of that work, there exist data sets where you have static pictures and people ask questions about the relationships between those items, and some of the same methods that we're applying to these simpler data sets like Clever, we're also applying increasingly to real world data sets. But one of the strengths of these kinds of Clever and Cleverer is you can have generate large data sets of really interesting questions that really kind of carve at the right joints and ask the right questions and push the field in the right direction. And currently there's no equivalent data set that would have enough counterfactual examples or predictive questions that you could ask that would be able to drive progress. In general, one comment I would make is that so much of the progress in AI has been driven by the creation of good data sets that organize our efforts. And I think, the Clever data set's a good example. We as part of the community are pushing forward this idea that really what we need to get towards are not just simple examples of taking a picture and telling what's in it, but rather answering these kind of harder, more nuanced questions about, what's going to happen next or what would have happened. And that's, I think, starting to get a much richer kinds of reasoning that are going to be really valuable as we think about applications of AI in the future.
So the NSCL, the neuro-symbolic concept learner, can be trained on this Cleverer data set as it was trained on the Clever data set. Is that right?
That's right. And when the Clever paper comes with a new neuro-symbolic dynamic learner, which includes models of the physics of the world. So the original question answering models didn't include any notion of time. They were built to work on static images.
Right.
But the way to think about it, you have a neural dynamics engine now that the system can rely on to model the interactions and the physics of different objects. And if you think about how we solve problems like this, if you asked a question, what would happen if we had removed this ball? What would the cube hit? When we think about how we solve those problems, introspectively, we actually imagine them, right? Like it's almost we do a simulation in our mind, and that simulation includes dynamics. So to solve this problem in the sort of neurosymbolic mold, we needed to add the team needed to add an additional piece, which was this dynamics engine. Sort of think of like a little physics engine or a little game engine, like the game engines that control video games, that the system can use to do these simulations. And then that's another sort of tool that's at the disposal of the symbolic system for answering these questions.
When a child pushes stuff off its high chair table, it's learning the laws of physics. For a computer system to learn that without it explicitly being coded, it has to infer that from multiple examples. Is that the sort of thing that's happening here? Or when you talk about a physics engine, does that have coded into it the laws of physics that are being applied?
Yeah, there's different ways you could do it, obviously. I mean, you could imagine building a system that has an innate understanding of physics and uses that to help it, reason about the world. You can also imagine building systems that learn the physics. They learn what happens when an object falls off the table. You can learn what happens when an object collides with another object. But I do believe that is exactly what's happening. When the baby's pushing things, moving objects around. It may be the case that they have some native knowledge of physics. You could imagine over evolutionary timescales they might have acquired the groundwork for some of those things to make it easy to learn. And that's, there's a debate between nativists and empiricists within the developmental psychology literature, sort of arguing over to what extent are these capacities, are you born with them, or to what extent do you learn them? Yeah. But leaving that aside, I think the broader question is this idea of, hey, I have a world, in front of me. I want to be able to, achieve goals in that world. I want to be able to predict what's going to happen in that world because it's going to impact me. I need to build a model of that world. And that model includes things like physics. And I can build that model in a couple of ways. I mean, to some extent, I could be born with that model, and you can imagine hard coding in some of the rules of physics. That might be one way to do it. You can imagine observing the world and learning new physics. So, things like magnets. Strong magnets probably didn't exist or weren't easy to find on evolutionary timescales when humans were first evolving, on the African savannah, but we are able to learn intuitions by working with these powerful magnets and seeing how they repel and attract and build a mental model of how that happens. Yeah. So we can learn by observing, and then of course we can learn by doing, and that's a big part of what the kids are doing. And we think that's important as well. The idea that you need to be able to have agents that go into the world and try things. You do little experiments, like what happens if I what happens if I knock my bottle off of my high chair? What happens if I take this object and I ram it into that object? Does it pass through? You can imagine interaction with the world as being a very, very valuable way of very quickly refining your model and building that mental model, which then you can use for the rest of your life to predict how the world's going to unfold, which is a valuable thing, to predict how to plan how you can take actions in the world to achieve some particular goal and, sort of simulate forward. If I did this, if I hadn't done that, what would happen? That's really the spirit of what Cleverer is really starting to try and get into.
Yeah. Is this the first set of its kind?
This is the first video reasoning data set like this. This is how the field moves. We define problems. We often define problems that are well short of the final goal. Clever is a great example of that. Then you solve it. Clever came from a group at Stanford and Facebook. The field solves the problem, and then you ratchet up the complexity and say, okay, well, now what we really want to get at is some of these other ideas. And of course, you can imagine this is a very impoverished, simple world with simple objects, with simple interactions. But where we're going is much more complex, richer worlds, 3D worlds with realistic physics, but also, abstract worlds as well. We want to build methods that aren't just about the sort of Newtonian physics and kinematics of the world, but also include things like, when you have an organization with people, you build a mental model of how does my organization function. Or if you have a machine, you have an internal mental model of how that machine functions. If you repair a car, you have a mental model of how the car functions and what different parts of the car do. And if something's broken, you use that internal model to think about what would you need to do to fix the car, right? And it turns out everything we do, when you really look at it, a huge fraction of what we're doing in our day-to-day jobs is about constantly refining our mental models of the world and then using those mental models to solve problems for our benefit. And that's kind of in a nutshell, almost everything we do. And, it also encapsulates an awful lot of what we'd like AI to help us with. They could go out there, form a mental model, a shared mental model, ideally with you, so that it can solve problems. It can show you what it's doing. And I think that's really the holy grail for what AI needs to do in the next couple decades. A lot of these ideas very, very naturally feed into robotics, right? Because robotics is all about, an agent with certain degrees of freedom interacting in the world. And, oftentimes one of the problems with robotics traditionally is you actually have to wait for the real world to unfold, right? Like the world, the actual reality that we live in, the physical reality we live in, has a certain clock to it, which is what it is. And you can't run the world faster than it's going to go. So people do a lot of simulation in robotics to start to get around this, and you have to take your simulation and transfer it to the real world. It's hard to get supervision, and having agents that can actually get out into the world and interact with the world and efficiently. Efficiency is key because you're running at the clock that the world natively runs at. To be able to have that model, to come up with the experiments you want to do, to either validate the model or refine the model. Ultimately to solve some sort of task. I think that's very much in the heart of everything we do. But I think it's much broader than just robotics too, right? I mean, I think you look at almost any problem we have in the world that we, on our day-to-day lives, try and solve. Think about things like climate change. We have we build models of the climate. We're trying to understand what's going to happen. We're going to do experiments to help refine that model. That loop of observe, interact, refine our internal model, and repeat is very, very powerful. And that's ultimately, I think, what we need to get into all of these different fields. What these neurosymbolic question answering approaches do is they take the question, which is natural language that we produce, and then turns it into a set of symbolic operations, a program. Yeah. And that program is now very precise. That's really what, in the neurosymbolic approaches, they use neural networks to go from the natural language into a symbolic representation, and then use neural networks to go from the image into a symbolic representation of what's in the image. Like what objects are there, what properties do they have, where are they in the scene. And then what you do is you take the program that you got from the question and you run it on the symbolic representation. So you're into the symbolic space, and you can even do things like running simulations. You have a deterministic or even a stochastic program that you can run that says, I'm going to simulate forward what would have happened if this object wasn't there. So really what the neurosymbolic is about is neural networks get from the real world, carving at the right joints, extracting the structure into a rich symbolic structured representation of the world. And then once you're there, you can then operate on it in very sophisticated ways. And Clever really, drives us one step closer to a world in which we can use those symbolic representations to simulate, both what will happen next, in a predictive mode, but also counterfactuals, what would have happened or what would I need to affect a particular kind of change. That's just the next step. There are many more steps that come after that, but that's really the direction that we're going.
Yeah, that's fascinating.
Yeah, I think the key idea here is that it's really about building models of the world. And that really is the unsupervised piece of this. How do you observe the world, interact with the world in a way that lets you build a model that lets you either solve problems, predict what's going to happen, do any number of things that are ultimately advantageous for us. As humans, we're trying to, survive and reproduce and get food and all that. We build a model of the world by observing passively, by interacting to refine that model. What we're interested in particular with this neurosymbolic idea, is that model, the best kind of model we can have, is a fundamentally symbolic one. It's about entities, their relationships. We can simulate in that symbolic world. We can apply logic, and that's a very powerful tool to mix with all of the power that comes from learning. And it can be certainly fundamentally unsupervised and self-supervised. You go out into the world, you have agents that can affect changes, that can do experiments, and we think that mixing those ideas together with symbolic ideas is very, very powerful.
That's it for this week's podcast. I want to thank David for his time. If you want to learn more about neuro-symbolic AI, you can find a transcript of this episode on our website, EyeOnAI. That's EYE-ON.AI. We love to hear from listeners, so feel free to contact us with comments or suggestions. And remember, the singularity may not be near, but AI is about to change your world, so pay attention.